Alright, in our last video we learned, our proof video we learned about what integrals were. Now we're going to learn what derivatives were. Okay, we're going to learn what derivatives were. Alright, so derivatives. More calculus. Okay. So integrals, like we said, was the area underneath the curve. All right, and so if we looked at our example before of the car, okay, the car was moving forward. Okay, we accelerated up to 66 feet per second. We held steady for 100 seconds, and then we dropped down. Actually, I'm going to draw this extra. I need the areas for this. Okay. All right. So we're going to start off. We started off at 0, went to 66. This is feet per second, time, rate. Okay. All right. And then we went to 66, then went back down to, this is 22 seconds, it's 122 seconds, and this is 133 seconds, right? Alright, T. This is R feet per second. Okay. Rate at feet per second. Time, seconds, rate, feet per second. Okay? Well, if I want to find my acceleration, what would I do? Well, I know that I went from 0, here I went from 0 to 66 feet per second. So here my acceleration is 66 feet. My acceleration is 66 feet per second. And we're going to divide this by the change in time, which is, let me do this a little bit differently. Need a steadier camera. 66 feet per second divided by 22 seconds, and we're going to see this is going to be equal 3 feet. Seconds times seconds is seconds squared. Or really, every second, my acceleration increases by 3 feet per second, okay? Well, what is this? Well, this is actually just the slope of this line, okay? The slope right here is going to be the slope of my line. All right? Conversely, this second one, we can see that what's my change in speed? Well, there is no change in speed. The second one, X. Ones. A is the change is going. A is going to be 66 minus 66 over 100, or it's going to equal to 0. Okay, and here my acceleration is going to equal, it's going to equal 66. Finally, 0 minus 66 over 11, and that's going to equal negative 6 feet per second squared. Okay, and we recognize these things. We're just finding delta y over delta x in some sense, right? It's really delta r over delta t. Okay. In this case, which is the slope, right? In this case, it's delta. Actually, it's delta r over delta t. All right, but it's going to equal the slope of the line. At the with a function, the integral is the area under the curve. The derivative is the slope of the line. The derivative is the slope of the line, okay? The integral is the area in the curve. The derivative is the slope of the line. Okay, and then to give ourselves that little bitty that another example here. Remember, we were doing the same thing. We were looking at this, and we said, well, it's probably assuming more along the lines of, let's go, wait, be closer. And then we have a whole bunch of data points all through this line. All right? Well, when the computer wants to find, we want to find the acceleration at each individual point, and we know the acceleration is simply equal to the change in velocity over time. And so we have here, we just have we have 2 points, right? We have these little rise and runs, okay? This circle's backwards, and this triangle, you can see all these triangles, okay? These are a bunch of triangles. Each individual triangle goes up. You know, this one's going to go down a little bit. All right, this one's up here somewhere, and this one's right there. Okay, all of these triangles are changes in velocity. Okay, and so we're simply going to take r of t2 minus the rate of t1 divided by t2 minus t1. Okay, and that's, of course, is going to give us the slope of the line over that little bitty point. And again, I'm not going to get into it right now, but when we do derivatives in the traditional sense, we're going to basically find the limit of these functions. And in this case, each individual derivative is different. Is just a set of data points, and so each individual derivative in this sense is simply this function of the difference between the two velocities over a short amount of time. With a function, we actually find another function that will always tell us what the derivative is at that point, and we'll get it later. But basically, the important part is understanding is that the derivative is the slope of the function, and in the way the computer would find it, and the way you can always find it, obviously, is simply by finding 2 points very close together, taking the difference, okay, and finding basically the slope of the line at that point.